Hey everybody, I want to tell you about inverse functions today, but to do that, I need to start by talking about function composition, which is, well, a thing we were doing at the end of the last video. So let me start doing that. So the idea of function composition is that you are putting one function inside another one, just like we did when we were talking about evaluating functions last time. So let me come up with two functions here. I'm going to say f of x is 2x plus 3, and g of x can be x squared minus 4. Okay, so those are my two functions. So what I'm going to do is I want to sort of identify a new operator, not a new operator. It's the thing we were doing last time. I want to find f of g of x, which, if you remember, is essentially the thing that we did last time, right? I took a function and I put it in for the variable in another function. That's what I'm doing again, except now I'm putting it, I'm just calling it g instead of x squared minus 4. This is exactly the same thing as this. Right? There's literally no difference between those things except how I wrote them, and the fact that that squared is absolutely sloppy as heck. So let's try that again. One more try. 2. Fine. Okay, so the way I'm going to do that is I'm just going to take x squared minus 4 and put it in for the x in f of x. So this is going to be f of, or excuse me, not f, 2 times x squared minus 4 plus 3. Right, I literally just replaced this x here with the x squared minus 4. That's all I did. And then I just simplify. So this is going to be 2x squared minus 8 plus 3, which is 2x squared minus 5. There you go. That's f of g. Now, a thing I want to point out is I can also find g of f. And you might think to yourself, oh, I bet it's the same. Turns out it's not. So let's see what g of f looks like. G of f of x is going to be 2x plus 3 squared minus 4. Notice that I'm putting f in for the x and g this time as opposed to the other way around. Right? The thing in the parentheses goes in for the variable in the thing outside the parentheses. So I'm going to multiply that all out. I'll just kind of do it real fast. So it's 4x squared plus 12x plus 9 minus 4, which is 4x squared plus 12x plus 5. All right, so that's f of g, and this is g of f. And they're different. And I hope that actually kind of makes sense to you, because I want to think about functions sort of as like as machines. So let's say that I have two functions, one of which puts on my shoes and the other one puts on my socks. So we're going to have shoes of J for Jeff, shoes of J and socks of J. Right? So in each case, it takes whatever state I'm currently in, that's J, and then it puts either shoes on my feet or socks on my feet, depending on which function we're doing. So let's see here. So if I have my two functions go something like this. And all right, I wish I could draw people, but I can't. So this is going to be shoes, and this is going to be socks. So if I start over here, and I go into the shoes machine, and I come out with shoes on, and then I go into the socks machine and come out with socks on top of my shoes, that has not gone well, right? That's not the order I want to run these machines in. I want to go into socks first and then shoes. So you can see that functions, it matters what order you do functions in some of the time. Most of the time it does. Once in a while it won't matter, but that's not the general case. So if I go left to right in this machine, I exit with my bare feet in shoes and socks on top of those, which is not ideal. So what I would instead like to do is I would like to do. So let's think of that. So here I'm doing shoes first and then socks, right? So if I do that, I get. Whoops, that's not what I meant to do. Hello. Sorry, Zoom's giving me a hard time. Hang on one second. Okay, so if I do shoes, so if how can I say this? The thing I do first is the thing that goes inside, right? So if I go back and look at this, what I'm really doing is I'm doing this function first and then taking the result of it and putting it into this function, right? So when I say do g of x, what I mean is I apply g to x and get this result. And I take that result and I put it into f. So the thing on the inside is the thing I'm doing first, and the thing on the outside is the thing I'm doing last, in exactly the same way as you would expect from PEMDAS, right? You do the inside parentheses first. So if I am doing socks of shoes, if I'm doing this, of shoes of j, that's bad. That comes out with socks on top of shoes, right? It puts on the shoes and then it puts on the socks. That's incorrect. What I instead want to do is shoes of socks, right? So this would be not the order I want to do this in. Instead, the order I would prefer is shoes of socks. Or the order I would prefer, in all honesty, is sandals, but that's not part of this. So in this case, I take my sock, I go into the sock putting on machine, and it puts socks on me, and then I go into the shoe putting on machine, and then it puts shoes on me, and that's great. That is happy me, wearing shoes properly, like any good kindergartner. So the point I'm rather clumsily attempting to make here is that the order matters. The order that you do a function in matters. And so you can't just, so like f of g is not the same thing as g of f. Now, you can do other things besides just like f of g. You can do f of f, for instance. So what was f? Was it 2x plus 3? I forgot my own function. 2x plus 3, okay. So if I have f of x is 2x plus 3, then I can do this, f of x, right? There's nothing saying that I can't take f of x and put it inside its own variable, because f of x is just 2x plus 3. So I could certainly find f of 2x plus 3, and it's sort of coincidence that f itself is 2x plus 3. That's a perfectly valid function that can go inside f. And so I get 2 times 2x plus 3 plus 3. It's 4x plus 6 plus 3 is 4x plus 9. There we go. There you go. You can do that as many times as you want, right? There's no theoretical limit to the number of times you can put a function into itself. I can do f of f of f if I want to. F of x. And there are actually times when it's really helpful to do this sort of thing, especially in science, like with repeated experimentation or generations in biology, right? You kind of feed one generation back into the previous one. Is a thing. Sorry, not with genetics is what I'm trying to say here. Well, I know what this bit is, right? This bit right here, the f of x is 4x plus 9. That's what I found. F of x is 4x plus 9. So this is really just f of 4x plus 9, right? Which is 2 times 4x plus 9 plus 3. Which is, what is that, 8x plus 21? 8x plus 21. There you go. And as you can guess, I could do this a bunch more times if I wanted to. Yeah, that's not super enlightening to do that operation a bunch. However, I will say this: there's like, if your function is simple enough, you can often find a pattern for the nth iteration of this, right? This is my third iteration of composition, right? So I could do something like this. Let's say I'm going to make h of x a new function here. It's going to be 2x. Yeah, let's do x plus 2. That'll be more interesting. X plus 2, or it'll be it'll be easier to grasp. So if h of x is x plus 2, the way you want to think of this is whatever you put into h adds 2 to it. So if you put 10 in, you get 12. You put 18 in, you get 20. Put -3 in, you get -1, right? It's plus 2, whatever you put in. So if I do h of x, right, this is x plus 2 plus 2. I want to think of this as doing h twice. Well, if h once is adding 2, then h twice is adding 4. And indeed, that is in fact what we see, right? This is x plus 4. Right? If I just drop the parentheses and simplify. If I do h of h, I bet you can guess what it is. Right? That's really just h 3 times, right? I'm taking x, putting it into h, and then putting that into h, and putting that into h. So I'm doing h 3 times to x. It's going to be x plus 6, right? So this is x plus 4 from the inside plus 2, which is x plus 6. So let me give you some notation here. So I would say that h to the n of x, and let's not use an n yet. Let's start with like a 4. Right, so that I don't have to write 4 h's, right? I could, but I think you see where this is going. And I'm sure you know what this is, right? This is going to be x plus 8, right? If I'm doing h 4 times, I'm doing I'm getting x plus 8. Oh, I'm sorry, I'm using the wrong notation. I apologize. That is actually the notation for something in calculus. That's the fourth derivative. This is the thing that I want, no parentheses there. I apologize. You probably didn't even notice, but let me give you the right notation. H to the fourth of x is doing h 4 times, right? So what is this? H to the n of x. That is adding 2 n times, right? This is x plus 2n. Right? When n is 1, I'm doing h 1 time, and I add 2. When this is 2, I'm doing h 2 times, and I'm adding 4. Right? So n would be 2, and I get 4. When n's 3, I'm adding 6. When n's 4, I'm adding 8. And so this is the general formula for doing h n times to something. Now, there's a really interesting branch of mathematics that deals with doing a function repeatedly over and over to itself that you have probably heard of. It's commonly called chaos theory. That turns out to use this a lot. That is not where we're going with this. I just wanted to show you this thing because it's function composition, right? I'm putting one function back into itself over and over and over again. And that's a fine thing to do. You may do that in some science application that you go on to in the future. Like I said, genetics uses this idea a lot. Other sciences do as well. That's not what I want to concentrate on. I just wanted to talk about function composition, which is putting a function inside another function, or sometimes inside itself. One more thing, one bit of notation that I won't use, but you might see in the future. So if I have f of g of x, you can also write this like this. And there's actually a perfectly good reason for this that I'm not going to go into now. I'm not going to use that notation because I find it generally confuses students. One, this looks like multiplication. It's not. It's composition that says take G and put it into F. But I think if you're trying to say take G and put it into F, this says that much better. And so this is the notation I'm going to use. I don't know if your book does this one or not. Some books do, and in the future you might very well see this. This is called the composition operator. It just means this. There's no difference between them. So I'm just going to use this one. Okay. that's all I want to say about composition. Composition takes a little bit of practice. You're very used to adding, subtracting, multiplying, dividing, and this is actually none of those things. This is a new operation that you likely never done before, and so don't be frustrated if it takes you a little while to adjust. It takes everybody a little while to adjust to something that's relatively simple, but this is one of those things that once you get it, the light bulb will go on and you'll just be able to do it no problem. So practice until you get this. But that's all composition is. You take one function, you put it into another function, or sometimes back into itself. Okay, the thing I really want to talk about are inverse functions, which is an idea you have actually used a lot, although you may or may not have called them that. So here's the idea of an inverse function, and I'm not going to get into how to calculate them right now. I just want to show you what they do. And we'll do a little bit of calculating, but mostly by thinking our way through something. So here is the idea. So I've got two sets of numbers. These guys are your x's, and these are your y's. So inputs and outputs, essentially. I don't want to think of them exactly as inputs and outputs because you're going to see why in just a second. F does that. F takes an x, right? It starts with a point in x, and then you do f to it. Starts with one of the x's, rather. You do f to it, and it ends up over here, a blue point. It started out as a black point. I don't know if that was obvious. Let me make it red, actually, so it's clearer. There we go. So I got this red point, this red x, and I do the function f to it, and it ends up as this blue y. I'm realizing right now that I should probably make f not blue itself. No, I'm okay with that, actually. I'm okay with that. I want to leave it as blue. Sorry. I'm having some second thoughts about my presentation here. So we take this function that we're calling f, and we do it to an x, and it gives us out a y. You knew that already. Now, there's another function, some of the time at least, that goes the other direction, that takes us back to where we started from, and that's f inverse. That's what inverse functions are. Inverse functions take an output and turn it back into an input. Or I said that badly, but that's the idea. So this is f inverse. This is not my smoothest presentation, but hopefully you get what I'm saying here. Whoop. That's what I get for trying to color code things. There. So I start with an x over here, with one of my x's. I do f to it, and f turns it blue, makes it a y. And then if I want to go back to where I started from, very specifically, like the exact point I started from, the function that does that is called f inverse, because it undoes what f did, right? If I have this point, like let's say this is A over here. A is this little red guy. And then B is this blue guy. So F takes red A and turns it into this blue B. F inverse takes in B and it gives me back out the exact thing I started with, or A. That means that F inverse is undoing what F did. That's the idea of an inverse function. And I said you've used these a bunch, and you have. We didn't really necessarily refer to them in this particular way, but let's say I was trying to solve this equation. Let's solve an even easier equation. Hello? X plus 3 equals 6. I have a good feeling that you can solve that equation in your head. However, the thing I want to point out is this. This plus 3 is something that we're doing to the x. It's a function. Adding a 3 to something is a function, as we saw with the x plus 2 bit a couple screens back. the way we undo adding 3 is subtracting 3. Minus 3 is the inverse of plus 3. So whenever you're solving an equation, you're actually using inverse functions all the time. And if I wanted to solve this, well, I've got a plus 3 that I need to cancel out, which is what inverses do. So I use the inverse. So that's the way in which you have used inverse functions before. And in fact, I want to go back to socks and shoes, right? So remember that I wanted to do shoes of socks of J, right? That would put on my socks and then put on my shoes, which is what I want to do. However, what if I wanted to take them off, right? So let's start simpler, right? So if I have socks of J and I want to turn that into just J, right? I want to not have I want to take in a me that has socks on and undo it and just get back to J. The thing I need is socks inverse, right? I need to do socks inverse of socks of J. So if this machine, the socks machine, puts socks onto me, socks inverse takes socks off. So here what I've got is I've got me, and I go into the socks machine, that's the inside parentheses, and I come out with socks on. And I go into the socks inverse machine, and I come out just me again. No socks. So this is the idea of sort of like a quote unquote real world inverse function. It just undoes whatever the initial function did. So if socks puts socks on, socks inverse takes socks off. That brings me to my next point, which is, what if I wanted to undo both things? What if I ran through the socks and shoes machine properly, right? So I put on socks, and then I went into the shoes machine and got shoes put on me. What if I wanted to undo that? Well, if I wanted to undo that operation, not only do I have to use shoes inverse and socks inverse, I have to use them in the other order. Because look at just think about yourself with your shoes and socks on, right? To put your shoes and socks on, you have to put on socks, then put on shoes. But to get back to bare feet, you have to take the shoes off first, even though they went on second. And you have to take the socks off second, even though they went on first. So it's like an onion, I guess. I don't know, something with layers, right? So what I have here is a bunch of layers of stuff on top of this J. And if I want to get rid of them, I have to take them off from the outside in, even though they went on inside out, right? We did socks first and then shoes, but to undo them, we have to do shoes inverse and then socks inverse, right? So let's say I wanted to get down to just J. So yeah, so I would do like, how do I want to say this? So let's say I've got shoes of socks. I wish I'd given these letters so I didn't have to write so many words of J. And then I want to get back down to bare feet. So to this whole thing, I would have to do shoes inverse. Because that would take the shoes off that are on the outside. They're in the outer layer. So those guys cancel, leaving me socks of J, which is to say, I have socks on now, but I don't want socks on. I want to have bare feet. So I have to do socks inverse to the result. Right? So I have to do socks inverse of socks of J. And that gives me just J. And this has been a long, kind of silly presentation of a thing that I've actually told you before, but I didn't tell you in this way, which was the reversed order for solving and simplifying. All right, remember PEMDAS. That's not how I want to write that, or where I want to write that. Let's try that again. There we go. PEMDAS. Simplify. When we are simplifying, we do the parentheses first, then the exponents, then multiplication, division, then addition, subtraction. Great, you already know that. That's what the acronym's for. On the other hand, when we are solving, we're actually going the other way, where we are peeling off one thing at a time to get back to just an x, usually, or some other variable, right? And so when we're simplifying, we do this order, but when we're solving, we actually have to undo the addition and subtraction first, then the multiplication and division second, and then the exponents in the parentheses. And let's do a really simple example of that to kind of cement that, right? So let's say I have 3x plus 6. I'm going to call that f of x. If I'm simplifying or evaluating, which is effectively the same thing here, if I wanted to do f of 2, I would do 3 times 2 plus 6. Notice the order I do that in. I do the multiplication first and then the addition second, right? This is 12. If I instead wanted to say f of x equals 7, find x, right? So I'm solving for x. Well, I would have 3x plus 6 equals 7. And in that case, I would not do the multiplication and division. I would not undo the multiplication and division first. I would instead undo the addition and subtraction first. Minus 6 minus 6, 3x equals 1. And then I would undo the multiplication, right? So I would do addition and then multiplication, undo it. All right, so this x is 1/3. That's because simplifying and solving are inverses of each other. No, it's not necessarily entirely obvious, but that is the case. Okay. Let me pause for 1 second here. I need to go check my notes. All right, glad I checked my notes. I had forgotten exactly what my next thing to say was. So here's what we want to do next. I want to talk about what the inverse of a function with more than one step looks like. Right, so f of x was 2x plus 3. I did not do that correctly, 2x plus 3. So f inverse of x is, what is it? Okay, so there's actually a relatively easy, or there's a algorithm for finding this. I'll give you the steps in the next video. We're not going to worry about it right now. I just want you to think about what this function is doing. Right, if I look at what f is doing, it is multiplying, it takes in whatever x is, it multiplies by 2 and adds 3 to it, right? So if I put in 2, I get out 7. Put in 18, I get out 39. You get the idea. But if it goes times 2 plus 3, then the inverse should do the opposite of that in the opposite order. You should go minus 3 divided by 2. Whatever goes into it, or whatever goes into the inverse, needs to have the opposite operations done in the opposite order to undo them. Or another way to think of it is, my inside, the first thing I'm doing here is the 2x, and then after that, then I'm doing the plus 3 to it. So what I want to do is peel off the layers one at a time to get down to just the x. I'm trying to peel off everything that's not x, essentially. And so the first thing I need to do is subtract 3 to get rid of the plus 3, and then divide by 2 to get rid of the times 2. And so you can kind of see it being undone. So I'm just going to write down what that is. I want to do, oops, where'd my, I think I'm on the eraser. I don't know how many times I've done that so far, but it's a bunch. Oh, come on, Zoom. Thank you. So I want to do, should undo times 2 plus 3. right? So it needs to, like, that's the order that f is doing things in, so it needs to do the opposite things in the opposite order. Therefore, oh, by the way, here's a little tip for you. Impress your math friend, or impress your math teachers. That symbol, the three dots in a triangle, equilateral triangle formation, means is mathematician shorthand for the word therefore. I don't know why, but it is. All right, so therefore, if I want to undo times 2 plus 3, I should do f inverse should do minus 3 divided by 2. Right? So if f does times 2 plus 3, right, puts on the socks and then the shoes, I need to take off the shoes and then the socks. And so I can actually write down what that is. I can say, well, okay, if I should do minus 3 first, well, it's going to take in at whatever goes into it, and it's going to subtract 3, and then it's going to take the result of that and divide it by 2. And that's f inverse. So that is, in fact, what f inverse is. It's x minus 3 over 2. And I'll show you how you can tell that by doing this. So if I do, I'm going to do the next screen. So I'm claiming that f of x is 2x plus 3, then f inverse of x has to be x minus 3 over 2. That's doing the opposite things in the opposite order. So what I'm going to do is I'm going to calculate f inverse of f of x. Right, I'm going to do some function composition. This is actually why we needed function composition first. So I'm going to take f and put it into f inverse. So this is the same thing as f inverse of 2x plus 3. Which is, I'm going to take 2x plus 3 and put it in for the x. So that's going to be 2x plus 3 minus 3 over 2. And you can see what's going to happen, right? Because of the way I constructed f inverse, well, the plus 3 and the minus 3 are going to cancel. And that's going to leave me with 2x over 2. And then the 2's are going to cancel, and that's going to leave me with just x. So f inverse of f of x is x. And that's actually one definition of what an inverse function is it's whatever function gives you back x after you do. So it's you take x and you do f to it. The inverse of that function is whatever gets you back to x, whatever you started with. And so you can kind of see how this function right here, the x plus 3 over 2, takes apart 2x plus 3 one layer at a time, right? It takes off the plus 3 and then it takes off the 2. Opposite operations in the opposite order. And lo and behold, you get x. Now, an interesting thing about functions, remember when I told you that in general, functions like f of g of x was not equal to g of f, right? It mattered what order you did your functions in. With inverses, if they are actually true inverses of each other, and there are some that aren't, I'll show you one that's not in a second that seems like it would be. If they're true inverses of each other, then you can do them in either order and it'll work both ways. This is one of the few instances of function composition being commutative. That's probably not the way I want to say that. This is one of the few instances where it doesn't matter what order you plug the functions into each other. So let me show you what I mean. So here I calculated f inverse of f. I'm going to calculate f of f inverse now. I'll do it on another page because we're running out of room. So if I did f of f inverse of x, right, that is f of x minus 3 over 2, which would be 2 times x minus 3 over 2 plus 3. And you can see what's going to happen here. 2's are going to cancel. We get back x again. Now, an interesting example of where this doesn't work is x squared. And I'll show you why that doesn't work in just a second. But first, I want to preface that by saying not every function has an inverse. You can't always undo what you did. And I'll show you why. Like you might think, well, I mean, clearly I can undo whatever thing I just did. Sort of. But there are functions where their inverse isn't a function. So let me show you what I mean. So let's say that f of x is x squared. Then I think it's pretty clear the thing that undoes squaring is square rooting, right? Then g of x is square root of x. Now, these are almost inverses of each other. They are kind of as close as you can get to being inverses without actually being them, and I'll show you why. So if I have f of a equals b, then it has to be the case that f inverse of b equals a. Right? That's the way inverse functions are defined. If that's too esoteric for you, remember that that was my original picture of what inverses did. Right? It was this. If f of a is b, so in other words, we start with a and we do f and we end up with b. That's what f of a equals b means. Then f inverse is the function that goes the other direction. It starts with the thing you ended up with and goes back to where you started from. So that's what we want inverses to do. So whatever number this is, if I do f to it, I get that number. If I do f inverse, I have to go back to where I started from. So let me show you an example. Let's say f of 3 equals 9. I think that's fair. If I then take f inverse of that result, f inverse of 9, that is square root of 9, which is 3. Right, good so far. However, what if I did f of negative 3? That would give me, well, when I square negative 3, I get 9. But when I do f inverse of 9, I already know what that gives me. F inverse of 9 is the square root of 9, which is 3. That's not what I started with. Right? These guys are different. That is an eraser. That is not what I meant to hit at all. Oh my God. I'm so sorry. I wish I knew how to edit video and you didn't have to watch me fumble like this. Okay, let's try that one more time. So this thing that I started with is not the thing I ended up with. So these two functions, square root x squared and square root of x, aren't quite inverses. We want them to be, right? It seems like one undoes what the other one does, but not exactly. And I'll show you what the problem is. So I'm going to show you with a graph because that's the best way I know how to do this. There's x squared. There are multiple things that I can put in that give me the same output. Remember, this is like the definition of a function, or the definition of a function. Forget the function thing. Let me just show you what I mean. There are two different values, let's say 3 and negative 3, that I can put into x squared to get out 9. Right? There's two different x's that give me the same y, which is fine. You can have a function that does that. There's no problem with that. The problem comes when you try to reverse the operation, right? When all you've got is the output and you want to know what input led to that, that's what the inverse is telling you. It says, okay, for this given output of 9, what did you start with, right? That's what f inverse wants to find. And we can't find it because there was more than one. So we don't know which one it was, right? Because all we know is, all f inverse knows is we've got a 9 to put into f inverse, and we have to come up with whatever thing we started with, but we can't because there's more than one, and we don't know which one it was. So that's the problem that you have. This function is called, or a function that doesn't have this property is called one-to-one. So x squared is not one-to-one. Not one-to-one. 1-to-1. Also written like this. And so what that means is that x squared does not have an inverse function. Do not interpret that as meaning that x squared does not have an inverse, because it does. It's just that its inverse is not a function. So the inverse of y equals x squared is x equals y squared. Let's go look at this. So if I have this, y equals x squared, that's a perfectly good function, and it has an inverse. It's just that its inverse is not a function. Its inverse is this. Where this follows the usual property of inverses, where if you reflect it through the line y equals x, that's the graph that you get when you reflect it is the graph of the inverse. So like this point right here goes to that point right there. And this point right here goes to that point right there. And this one right here maps to that one, right? And so y equals x squared does have an inverse, but the inverse isn't a function. Because its inverse does not pass the vertical line test. And the reason its inverse doesn't pass the vertical line test is because x squared itself doesn't pass the horizontal line test, right? So this x equals y squared has a vertical line that goes through more than one point. And it has that because y equals x squared has a horizontal line that goes through more than one point. So what we say in general is that a function that is not one-to-one, which is one that passes the horizontal line test. So a function is one-to-one if it passes the horizontal line test. Y equals x squared is not one-to-one because it does not pass the horizontal line test. It does not. It has a horizontal line that hits it at more than one point. So if a function is not one-to-one like y equals x squared isn't, we say that it is not invertible, that it does not have an inverse function. It is a function whose inverse is not a function. So what we can do about that, by the way, is the thing that we actually do about that, which is we restrict the domain. And here's what I mean. I have y equals x squared. So let's look at this and this. Okay. If I want to have no horizontal lines hit more than once, what I can do is restrict the part of this function that I am willing to consider. So that horizontal line hits more than once, that makes it not a non-invertible function, or a function whose function is not an inverse, whose inverse is not a function. Oh my gosh, sorry. What I can do is, instead of looking at the entirety of the function, I can just do that. I can look at only this part of it. So this is y equals x squared, where x is greater than or equal to 0. Right? So this right here is a domain restriction. This is a function, or excuse me, this function is one-to-one. No matter where I draw a horizontal line, it only hits this part, or this part of the graph, in one spot. Its inverse is y equals the square root of x. So this function right here, and you can see that those things are reflections of each other through the line y equals x, as expected. So what's I'm trying to say here? If we restrict the domain of our function to where it is one-to-one, and that, so one-to-one, by the way, you can tell something is one-to-one if it doesn't wiggle about up and down, it just either goes all up or all down. Right? So like this function is one-to-one, this one is one-to-one, this is one-to-one, right? Even though it's kind of going up slowly at the end, it's still going up. this is not 1-to-1, and this is not 1-to-1. Right? Anything that goes up and down is not going to be 1-to-1, whereas anything that goes just up or just down is. So if you want to know where to restrict your domain, well, you just look at the parts that are going all up or all down and restrict it to that. If you go on to trigonometry, this is going to turn out to be surprisingly useful information. If you don't, I don't know how useful it'll be too, but that is how you determine what your domain restriction should be. And if you have trouble remembering that, think about x squared and square root of x. This is y equals root x. And why we restrict the domain of x squared to be just positive numbers if we want it to have an inverse, which we do. So that's the idea of 1-to-1. 1-to-oneness means a 1-to-1 function has an inverse that is also a function. A non-1-to-1 function has an inverse that is not a function. Every function and relation has an inverse. You just switch the x's and y's, and that gives you your inverse. Not every function has an inverse that is a function, right? Y equals x squared does not have an inverse that is a function. Its inverse is a relation, but not a function. I think that is the last thing I wanted to say about the idea of inverses. So let me stop sharing for a second. Pause the recording. I'm gonna look at my notes for a second. Yep, that's all I wanted to say. All right, fantastic. I'm gonna go ahead and end the video, and I'll see you guys in the next one.